We go.
Kick it off.
Here we go. Hi, everybody. Welcome back to Telescope Talk Pro, the professional edition. My name is Tony Darnell. I'm from deepastronomy.space, right down there. And today we are going to be talking with members of the professional division of OPT telescopes. In particular, we have Chris Hendren with us, who deals with... You're not up yet. I'll get you. He deals with lots of professionals. He helps NASA. He helps set up SpaceX and a lot of other companies. And so we're going to talk to him about what professional equipment is available off the shelf. But before I start, let me bring up my co-host Christian ready. What we had hoped to do today was stream on both of our channels. And when I turned the stream on, nothing happened on Christian's channel. So we've got some testing to do. But anyway, hi, Christian. It's good to see you. Thanks for joining.
Thank you, Tony, for having me back on. And thanks so much, everyone, for tuning in. Hopefully you're joining us here on Deep Astronomy. I put a link in my stream to join us over here. So thank you for having me back, Tony. And we'll get this sorted out one day.
Yeah, we will. I need to put on the auto live because when I push buttons and nothing
It's an experiment.
Yeah, okay. All right, well, here we are. And now I've got all of us up here. Joining me off to my left. I knew that would happen. There we go. That way. That way.
Other left.
Yeah, the other left. Chris Hendren. You know, you're flipped and you're turned around in videos and you never know which way is up. So anyway, hi, Chris, and welcome to our hangout.
Oh, it's great to be here. I've been hearing quite a bit from Dustin and Ian here about these live streams, and it's just been a huge honor to be able to come on and talk to both of you about what we do in the professional services division here at OPT.
Well, what do you do in that? So let's start with that. What do you guys do overall?
Well, professional services essentially covers all kinds of institutional sales. We do sales directly to government agencies. NASA was mentioned, the branches of the military for certain projects. We work with subcontractors with them, major DoD corporations, as well as commercial companies doing both space situational awareness or working with educational institutions for science projects or instructional projects. And then lastly, we have our education, which is a huge aspect of that. We work with everything from elementary schools all the way up to universities like MIT and others all over the world on getting research quality equipment in their hands, both for student teaching as well as actual research.
What is the main difference between a professional quality piece of equipment that you guys might have off the shelf and consumer grade stuff? Is it because I've been in plenty of places where I've seen Meade 12-inch LX200s or Celestrons set up inside institutions, and consumer grade equipment is possible to do research with. What's the difference, though, between that and what, say, a university might want?
Well, funny thing is we still have some universities that think that's the way to go just because that's the way it was done over the last 2 decades. And they're not wrong. You can do research with consumer grade equipment, but you're kind of fighting uphill to do it. So the thing you're going to have with research grade equipment, it's going to be built to much higher tolerances. The mounts will have more accurate drives. They're going to have oftentimes integrated computer programs to get the most out of the mount. Whereas with, say, an off-the-shelf consumer-grade product, you're basically, here's your telescope, go find some third-party program to run it to get the most out of it. The optical quality of the telescope parts tends to be much higher, and it's geared around collecting scientific data. And there's some specifics on that we can get into. Don't want to get too technical too soon here. Don't want to scare any people off the feed right away. But and then there are various aspects. There's either you're trying to record something that's short-lived or fast-moving, sometimes man-made. You're trying to collect data on stars, galaxies, supernovas, things like that, or you're trying to do spectroscopy, which you're actually looking at the fingerprints of the star So there's a number of different things that people do. And so I would say the one overarching thing is quality is huge for pro services level equipment, and then the complexity. And that's where we come on board, because oftentimes it's not just buy brand X product and you're set. You're getting a camera from one manufacturer, a mount from another, a telescope from another. You're talking a focuser from a fourth company. Sometimes we have to call a machinist to make custom parts when they're not commercially available for these customers. And that's kind of the pro services difference, is we don't just say, here's your scope, camera, and mount, figure it out. We actually will contact the machinist or come up with a complete solution. So that's the other aspect of professional services is the service.
So you're building essentially a custom research facility depending upon the scientific requirements of the institution. Is that right?
Not necessarily. I mean, because a lot of it can be done with off-the-shelf products. But say we had, we work with some advanced amateurs as well. And I have a fairly advanced amateur who wanted a big observatory near his second home out in the dark areas of East San Diego County. And he wanted a 24-inch telescope. So when you're talking like that, you have a lot of aspects. You have the telescope itself. You have the mount. You have to figure out how it's going to be protected, what structure it's going in, a dome or a roll-off. You have to have that discussion. With something so large, you have to make sure it's not going to run into the walls when you install it, because you have a telescope that's almost 4 feet long swinging around in there.
Right.
So
my wife has to take the same precautions, just so you know, that I don't run into the walls.
Yeah.
My wife would never let me set up a telescope. She would make me call you.
So let me ask you this: we always hear about NASA whenever all the spin-off technology that comes from NASA exploring space, building telescopes, building satellites, and taking people to the moon and space station, all of that kind of stuff, the space shuttle. They often tout their trickle down or what they call NASA spin-off technology, things that, yes, we use this to go to the moon, but it's also usable for all of these other things. And certainly, I'm starting to think that in the world of professional astronomy, not just NASA, but the professional community as a whole, if you think about it, often everybody that I know, we've often said that the future of astronomy is in the infrared. And the reason for that was that's where all of the interesting things are in the universe that we look at, especially the faraway galaxies and things like that. They've all redshifted into the infrared. But what has made that really a golden age is the fact that we now have detectors that are sensitive to the wavelengths that we need to look at. They're generally made out of mercad telluride, but there's lots of other components that go into these chips. And and so is it your experience that this has happened, that a professional grade camera might be built by, say, the National Science Foundation for the use of a certain telescope, but that technology has made it into an area that you can build and sell off-the-shelf components with? Have you noticed
more or
that?
less? I will say, we do get inquiries for both high sensitivity silicon sensors, which we do deal with, and for various reasons, things like gallium arsenide sensors that we don't deal with a lot of. One of the things that we do have to, we do come across, a lot of people think of consumer telescopes more as a hobby or a toy. When you get up to the professional level, these are tools. And as such, government agencies know they can be used for more than just astronomy. So you talk about something that can be used for infrared. There's a lot of things that give off heat signatures, human bodies, ballistic launches, things like that. So you have to be very careful and have a conversation about what they're going for. We deal more in the infrared on the telescope side. We work with optical shops that do custom coatings, typically protected gold because it has extended sensitivity out to like 10 microns. So deep into long wave infrared.
Which is why they coated JWST in gold as well.
Exactly. Exactly. They're not doing it to just drive up NASA's budget here. They're doing it because, common aluminum, especially when it's enhanced or overcoated, tends to fall apart in the near infrared a little bit. The dielectric coatings, which give you really high sensitivity, like 99% reflectivity in the visual spectrum, plummet once you get into NIR. And so we've actually had companies that will buy a telescope and have us send it to an optical shop, strip the coating off, and put either a single layer aluminum if they're going into shortwave or near infrared, or protected gold if they're going into farther wavelengths.
And so do you find that, and so it sounds like that's actually happened, that these technologies are sort of trickling down into areas where now more people can make use of these science cases, because in a professional realm, what generally happens is the science drives the technology, and they define what they want for, what exactly do they want to learn, and what do they need built to learn it, and so they go out and build. To what extent then do you think that is not necessary anymore, that these professionals now can just call you up and say, here is our program, here's our proposal, here's our NSF grant, whatever it is. We need a camera and a telescope optical train to do the following science case. Do you ever get those kind of calls from them where you're asked to put together an instrument for a specific science goal?
Generally, just because of Commerce Department and Defense Department regulations, a lot of times when they bring to us a specific proposal, there are restrictions on what they can and can't talk to us about. So, not to sound all mystical about that, but we can infer the information based off of what they want and the wavelength range they want to detect, but they don't necessarily tell us the purpose for it. Our goal is to be the conduit. We are the solutions company. We're not the manufacturer. So we contact manufacturers in the US, some companies in Europe as well, and we'll say, we have a customer that has specific requirements for this optical design. They tell us the design, how big a field they need, what wavelength range they need it to cover. And then a lot of times, those are the goals we are meeting. They won't tell us that we're trying to measure redshift beyond the visual spectrum. We can infer that depending on our conversations with the customer, but our goal is to just get the customer.
I wonder what's the big deal. I mean, why not just say,
well,
we want.
I mean, if they're saying, hey, we want to use this telescope to spy on, Russian agents or something like that crossing the border, whatever. Yeah.
Oh, sure. I'm not talking about the NSA or those kind of.
Right.
Yeah.
Right. But I think that's what that's your point, right, Chris? You're saying they can't give you the specific reason if it's classified.
Yes.
Oh, I know, but the dark energy survey could, for example, right? That's what I guess.
The dark energy survey could, but I guess what you're saying, Chris, if I may understand it right, if a government customer says, "Look, we can't tell you what the use is for, but we can tell you, okay, here's the waveband we want to search. We want to be able to search, and here's the field that we want. This is the sensitivity we want to do these kinds of integration times, etc. Make it happen." That's enough for you to go on. You can go ahead and say, no problem. I can.
Yeah, we will get in contact with the manufacturers that can make or modify an existing product to suit the customer's needs. But we will see that if it's especially related to DoD, they're going to be pretty tight-lipped with details. Even commercial companies, because there's intellectual property involved and things like that.
True.
They will tell us, we need this piece of equipment, and we need it with gold coatings, and then we work out the information. Usually we can work out, if not the camera they're using, at least the dimensions, because we have to work out the adapter chain so everything comes into focus properly when they get it. But that's the nature of the conversation. Unfortunately, in a post 9/11 world, it's the reality when you're dealing with these things. Yeah. There's a lot of products that are classified what's called dual use. by the government. And that means that it is so sophisticated that it can be used to track comets, or it can be used to track missile launches. They're that good. And so we have to be very careful if it's a U.S. government agency, if it's a U.S. company, if it's a product that's staying within the bounds of the United States or certain other countries, then we have a lot less of a hurdle to go over. We have certain areas of the world where it doesn't matter who's asking. We have to tell them, no, we can't supply that to your area of the world because of government regulations.
Right.
Yeah, I guess I see that, but it's still, I was, and I guess that'll actually prevent what I was hoping would happen, is this sort of trickle down effect for when you've, for example, I just want to give a quick example. Well, one of the things we needed to do was, when I was working at the High Altitude Observatory, was measure the, we were trying to measure the magnetic field of the sun. And to do that, we used these liquid crystal variable retarders to measure polarization coming out of the sun. And this did not exist anywhere else. But these liquid crystal variable retarders, they work really well. They change their retardance based on a little tiny current that goes in, and you can. It's identical to changing the polarization angle of a polarizer, and you can do that at 30 hertz, right? And so you can. This was something that I thought was really cool. It was a filter to look at the sun. And it was, I thought would be something that would, if we could build it and market it, it would sell for a lot of, it would be very useful to a lot of other people also trying to measure the magnetic field of the sun. But what you're saying is, yes, that's possible. And yes, it happens, but there are other constraints. It would have to be, I guess, looked at by the government to decide if it's a dual use. That depends on the exact nature of it, yes. And I don't mean to make it into this big, like I said, roadblock here. But we have to consider, again, the vast majority of the people that are contacting us. Right. When we get a contact from, say, Caltech or NASA, they're not trying to replicate the stuff that they have their own engineers for. They're essentially trying to do prototyping, test cases, things like that.
Okay.
Or cases where they have a project with a budget that requires what's called COTS, commercial off-the-shelf product, or minor modifications. And again, the vast majority of research, you have to remember, there are a few pinnacle universities, and there are researchers all over the world who are getting time on Hubble, getting time on Keck, and other things like that, or devising these new experimental research procedures using this equipment. But then you have a vast number of community colleges and four-year universities that are trying to train the scientists of tomorrow. And that generally starts in the undergrad, and it starts with equipment for measuring variable stars photometrically. It starts with using a spectrograph to get a fingerprint of a fast-moving star, measure the redshift of a spectroscopic binary. So that's
basic meat and potatoes type of astronomy, really.
Exactly, and there are more of it. Again, you say meat and potatoes, but a lot of people
been there, done that.
they don't understand that, even at the university level. A lot of people. That's why they're buying older design fork mounts, because their idea of an astronomy 100 class is, let's take the telescope out and do like a little class star party, which is fantastic to get outreach going. But it's really the possibility of understanding that as prices come down, circling back around to what you mentioned, Tony, before, the trickle down comes in computing power. It comes in sensor design. It comes down to the level of technology that is available to the advanced amateur or institution, without getting into, $500,000 grants and research studies.
I can imagine that it saves quite a bit of money.
If I could also just add, though, to that, Chris, it sounds like what you're saying, though, is that you're talking about the application to teach, undergraduates or even non-major like non-physics or astrophysics majors. But even at like an institution like where I'm at, it's a 4-year institution. We do research here, and we're in Towson, Maryland. We're essentially in the city, and we actually do research with the.
Oh, absolutely. Absolutely.
So I'm sure you're able to supply those customers. Like, we're not Caltech. We're not going to say, well, we would go up to our telescope up on the mountain atop Hawaii, but we just rather buy something off the shelf. No, we're gonna make a real investment in something like that.
Oh, absolutely. And you're not necessarily going to put it in Maryland. That's the other thing.
We might operate it robotically. Yeah,
exactly. And that's become much more available without those extremely high custom systems that were kind of the norm 20 years ago. You're able to get a telescope, a dome, using a standard computer, CCD camera. You can run it completely remotely. Dustin has shown with his observatory that you're able to do that just for the sort of aesthetic, pretty picture imaging, but it can be done for science and to allow sometimes multiple universities share resources for a particular telescope if they're in an area or in a group for sharing resources.
So when a university comes to you, this kind of goes back to my original question. I said that, so you basically essentially build systems, and you said you don't really build them, but I think I know what you mean. Like, you don't actually, you're basically leveraging what other manufacturers are putting together, but you're kind of integrating them together to build the final product and deliver that and support it. When a university or any organization, I'll just say that, right, be it an amateur or a university or what have you, says, well, here's the kinds of science that we want to do. Do you find that they mostly come to you saying, okay, we know what we want. We need, this telescope, this aperture, this focal length, these instruments. Do they kind of come to you with a pretty finalized set of requirements, or do you find yourself sometimes you end up kind of going back and forth and, tell me about your science requirements. What is it that you're trying to accomplish? What are your constraints? Like, how do you approach a project like that?
It's mixed. It depends on who we're talking to. If we're starting the conversation with the purchasing agent who may know nothing about astronomy, or if we're starting the conversation with the end user, we have schools that are well informed and they have resources, and they'll contact us and say, we need this specific system. And most of what we do at that point is clarify that, we'll run the numbers, make sure the camera's going to come to focus, make sure everything is going to work together. There aren't going to be any conflicts. We have other cases where they come to us either with a budget or a goal. They want to do photometry, either because they're partnering with an organization like the AAVSO or their
Association of Variable Star
Observers. Yep. We actually get a lot of interest from universities on doing, variable star measurements. And I realize that to a number of people, that's not necessarily cutting edge science, but that's the way to inspire the next generation of scientists. That's the way to actually realize that they took a picture with the camera through this telescope, and they can, using B minus V subtraction, they can generate a Hertzsprung-Russell diagram. They can actually take measurements, figure out where the roll-off point in the giant asymptote point is. They can actually determine within an order of magnitude how old that star cluster is. So they can take a picture that they have and generate real information out of it.
That's science, Yeah, that absolutely is science.
Yeah,
that's cool.
Let me just read. Let me just read a quick question from Sub Masher. Mishra. We were talking about gold plating, and he goes, "Why protective gold?" And the reason for that is it is reflective in infrared, and that is
absolutely.
You want to match your coatings and your mirrors and all of that, and your filters with the wavelengths that you're looking at for the most photons possible. And if you want the most infrared photons possible, you use gold coatings on the mirrors. Now, when NASA talks about JWST, they say that, and then they're so worried that because it's already an $8.5 billion thing, so they're like, but hold on. The gold is only one atom thick. So, it's not very, he said, all the gold on all of the segments of the entire JWST primary is less than some, I don't know, some stupid amount. It's not
less
even
than a wedding band.
Yeah. It's not. So it's funny to watch them about it because there's
not much gold on there at all.
Yeah, they're very defensive.
Well, that's one of the things that I've talked to one of the major partners we have here in Pro Services is PlaneWave Telescopes, which is based out of California, and they build.
I was going to say, just for our audience, can you help us understand who PlaneWave are?
Yeah, PlaneWave got started with a couple of the top optical engineers from Celestron back. They were there for quite a long time, and they had this idea of really going into the next step of professional and advanced amateur telescopes with a half-meter system. That's what they started with in about 2007. They have been partnering with OPT since then. They now build telescopes as small as a 12.5 inch, which is around a 0.3 meter, all the way up to a 1 meter, completely robotic system using direct drives and a really innovative corrected Dahl-Kirkham-Cassegrain design, which gives you a massive flat field. So it's actually changed the way a lot of institutions think about telescope design with them coming out. But the one thing I was told by one of the people there is when you're talking about optical coatings, they test their optics both before the coating is applied and afterward. And they have exceedingly high standards. When you're talking about differences in nanometers of thickness will actually change the optical figure of the telescope. So one of the things that comes up when talking about how good is an optic is what's called wavefront. And what that means is you're literally talking about what fraction of a wavelength of light the error on that telescope mirror is. So minimum acceptable is around 1/4 wavelength of light. If you measure it in the green at around 500 nanometers, that's saying you can't accept errors beyond about 125 nanometers anywhere on that mirror. And that is for barely acceptable commercial optics. Once you get into the professional realm, you're talking single-digit nanometers or less. So just the difference in the vacuum coating application of the gold or whatever metal you put on the glass can drastically change the way light focuses or scatters. If it's thicker in some areas by a few nanometers, the telescope won't produce as sharp an image.
That's pretty cool. That's legit. That's fantastic.
Peter Quinn wants to. Oh, did you say something?
I said I wish we had one here. Give me one. Anyway. Black Friday is a week from Friday, so if you want to get that research scientist in your life, something special, where would they go? How would they kick off the conversation? Go to opttelescopes.com and then just start shopping, or
yeah, it's optcorp.com, CORP like corporation. Okay. We have a pro services portal on there, and it's sort of a curated list of the higher grade products that we see most searched by institutions, schools, government, and the like. So we have telescopes of the Ricci-Chretien variety, the same optical design as Hubble and a number of other well-known research organizations. We have the PlaneWave, and that's PLANE wave, as in a flat plane, in we're bringing all the light together in a perfectly flat plane. That was the whole idea. No deviations.
Nice.
We have PlaneWave also makes high sensitivity and accuracy tracking mounts. And we have a number of different camera manufacturers. So I would definitely recommend checking that out. We have products at all ranges from people just getting into the hobby, space enthusiasts who just want to get a telescope and go see the night sky, to people who want to set up completely remote automated observatories, sometimes in other states, and conduct research on anything from supernova hunts, asteroid light curves, to advanced shell spectroscopy.
That raises an interesting point. You're talking about locating telescopes remotely. Obviously, trying to get around the bane of our existence, two banes, light pollution and water vapor, right? So we want to locate these telescopes in dark, dry skies.
Mm-hmm.
Now,
well, there's a third bane that people don't just necessarily consider.
Go ahead, please.
Air turbulence.
Yes.
And that is huge. It does come into play with elevation. You raise elevation, you generally decrease the amount of atmosphere and the water vapor as well.
Right.
But what you have to consider is they don't put telescopes where they put them necessarily because it's always the darkest location. I mean, that's ideal. Right. But you have to look at where the air is the most stable. When you get to these very large optics, air turbulence is fatal for recording detail. That's when you have to invest in very expensive adaptive optic system to try to overcome the atmosphere. A lot of people don't know this. The most stable air generally on the west coast of the United States here is up at Mount Wilson, which of course overlooks this huge valley with Los Angeles below it. The light pollution's terrible. However, on good nights up there, they get seeing turbulence at about 1/3 of an arc second. And so a lot of
that's pretty good.
A lot of high resolution planetary and speckle interferometry research is done there, just because of how stable the air is.
But do you offer, or are there in fact off the shelf adaptive optic systems that work on smaller telescopes like what you would be offering?
There is, to a degree. Now we have to draw a line between what is true adaptive optics, where you're actually deforming a mirror or optic, and what it should probably be termed active optics, which is usually a 2-axis tip tilt system.
Right.
The adaptive optics, we've looked into working with a few companies, and we have a few companies we've spoken to who may be able to do that. But most universities haven't really wanted to approach that, because at that point you really are talking like $500,000 system to properly integrate that. Custom software, actuators to move this piece of glass 2,000 times a second. And schools generally don't have that kind of budget around. Right. However, active optics can be had for some cameras as little as $800 or $900. And
can you help? Can you describe? You described adaptive optics with deforming a mirror.
Sure.
Tell us about the active or the tip tilt mechanism.
Sure, absolutely. So what you do is instead of using a laser to generate an artificial star, you're using your guiding camera. And for those of you who don't know, generally when you're taking advanced astrophotography, you have 2 cameras. You have the main camera, which is recording a long integration time. And you have a secondary camera whose only goal is to keep a single star at the same XY coordinate on the sensor. So what you do, you're already recording light to send commands to the mount to move every few seconds. But now you have to move the mass of the entire telescope. You have imperfections. You have sagging due to gravity, the flexure of the system. You have hysteresis of the motors. You have sometimes hundreds of pounds you have to move around in order to make a correction. And that takes time, and there are errors that accumulate. So what you do with an active optic system, you have a little tiny box that's right about this big, actually. It moves a piece of glass that might be 2 or 3 inches in diameter at up to 40 actuations per second. And so it takes the light from that secondary camera, which is at the same focus position as the main camera. And if it sees the light from the star move, instead of sending a signal to move the entire apparatus, it's just moving the piece of glass and using the refraction property of that piece of glass to keep the light focused at the same pixel on the main camera.
Wow. Nice.
But that does not change the wavefront at all that's coming in. So
that's correct.
If you still got bad seeing, it's not going to correct for that. It's just going to allow you to keep things more precisely positioned on the CCD itself.
Well, over the when you're talking the equipment up to say 0.5 meter to 1 meter systems, and when you're talking about the fairly narrow angle of sky that you cover, under normal circumstances, even doing that can yield a 30 to 40% improvement in the full width half max measurements of stars, being how tight the star images are, how bright they are. And sorry if I threw anybody with that term, but that's the term that gets used a lot in amateur astronomy to measure how good your focus is. So if you imagine the brightness of a star kind of like a bell curve, if you're plotting it from left to right across the image, well, the better your focus is. Yeah, there you go. So you look at a bell curve. So if you have a poor focus, your bell curve is going to be short and squat and wide. If you have a good focus and good seeing, you're going to have a very tall, narrow spike. So full width at half max essentially just means how many pixels wide is your star at half of its maximum brightness. So the smaller that number is, the better the focus is. And when you're using active optics, the whole idea is to keep that light centered on the smallest possible unit of the chip. Yeah, just like that second graph. And that's putting that star's intensity on a smaller part of the sensor, which allows you to gather your data in less time and get a higher resolution result.
Good. I think we should always have a blackboard now. I
was going to say, I am so glad I stayed at school today.
Yeah. I always want that now. In fact, I'm going to put one behind me just in case, because there's been times I'm sitting here gyrating with my fingers.
Graphics on the fly.
That's right.
Happened. Yeah.
That's perfect.
I have to laugh at Larry Keys' comment. He's like, Meade sold me an adaptive/active optics. What did I buy?
Larry,
how much did you spend, first of all, without asking what you got?
Larry, did they also include a bag of magic beans?
No, so do you know, do you know, Chris, what he got? Did they sell that? They sell active optics there too, right?
Not per se, not unless they're selling something that was made by another brand. The big two, at least in the amateur realm, are SBIG, Santa Barbara Instrument Group, and they're actually based out of Toronto area now. And then we also have Starlight Express, which is based out of the UK, but actually has a distribution point that we work with closely just up in the LA area. And so those are the two companies that generally have focused on bringing this to the amateur. The big question I would have is, okay, you have an active optics system. What camera comes with it? Because that's the other half of the equation. The little box with the glass in it doesn't do anything until you send it a signal from the guide camera to actually tell it what to do.
Right.
So that's more of a hardware software question with other bits of equipment. And that's honestly what we do a lot in pro services. It's not someone says, I want to use this telescope, or I want to have a system that does adaptive optics. Now we got to ask questions. What kind of camera is it going to be used with it? What telescope is it going to be on? Then I start running the calculations. Okay, what is your resolution in arc seconds per pixel? And what site are you going to put this telescope at? What geographic location? As Christian was mentioning before, you have water vapor, you have light pollution, and you have air turbulence. And all of that has to be carefully considered for siting a telescope. Again, for a lot of universities, sometimes it's more convenient to put it on the grounds. There's less of a liability there if something happens. But, we do have advanced amateurs as well as institutions that are logging into the internet and running their system from sometimes the other side of the world.
Larry, I think what we're going to do, Larry, at some point is we're going to get you set up with a camera, and I'm going to ask you into the Hangout. I want to see all the stuff you bought. He said, by the way, his camera wasn't as big. So you bought some nice stuff, Larry, and we need to get you using it.
Absolutely.
Because, it's every time we do these Hangouts, he's got a question about this didn't work, that didn't work. He's struggling with it.
He's got some gear.
He's got some serious gear, and we need to get him set up to use it.
Absolutely.
Properly.
Yeah.
So, that I'm going to do that, Larry. We're going to get you set up. So he's in Colorado. We're going to have to get him we're gonna have to get him on here and help him out, get him all
Certainly.
set up.
There's some support.
Okay, and Adam Synergy was asking a kind of a cool question. Where was it? If I happen to have a defunct radio communications dish, can I get a radio telescope? Actually, it's not really related to what we're talking about, but I'll just answer it real quick. I saw something on the internet that I think was true, that where you could take an old DirecTV receiver and do some science with that. I don't remember what frequencies it listened to, but it is possible. People are doing it.
It is. It's a small dish and a short antenna, so it was pretty high frequency, if I recall. It was, I think, something in gigahertz range. So, because that's what that satellite was designed for. That's what the dish was designed to receive in signals from satellites overhead. But yeah, it is possible. I've actually seen that article.
Yeah. Okay. So I don't remember much about it other than I was trying to figure out if it was recyclable, because I canceled my subscription and I leave you with the dish, right? And so I'm like, what can I do with this thing? And I was looking around and I just saw that.
Search for FRBs, Tony. Oh.
Yeah,
there you go.
That's right. Yeah, get that mystery solved. So, Chris, can you give us some dirt? I mean, your customers are really cool. You've got NASA, you've got MIT. You said you've got SpaceX. What do these guys buy? What kind of stuff do they get from you? Can you tell us?
I can tell you the stuff that I'm not under NDA about, certainly, but in general,
NDA stuff. Ooh.
Yeah.
Oh yeah.
So,
not surprising.
All right. Don't disclose any. You don't want to get you in trouble. But what can you tell us? What kind of stuff does SpaceX use from you guys?
Yeah.
Generally speaking, they're doing a lot of bench tests on optical benches with these. So not every telescope we sell winds up pointed at the night sky, remember. A lot of them get used for industrial purposes. They can be used either for collimating other devices that they're building, which is aligning the rays of light to make sure that everything's precisely aligned. Other aspects are proof of concept. So we do see a lot of interest. I'll say this, and I don't think I'm stepping on any toes saying this. We see a number of commercial and government institutions interested in our TPO line of Ricci-Chretien telescopes. It's an OEM brand that we have that's through OPT. It was kind of a joke. When we got contacted by this company, we needed to come up with a name for it. So TPO is Third Planet Optics, but it's OPT backwards. So
Nice.
but they actually make a line of very affordable Ricci-Chretien design telescopes, starting from a 6-inch RC design, 6-inch f9, which is $400. Any consumer can get that if they want to do imaging, up to a 16-inch, which runs around $7,000. It's actually a carbon fiber truss with they use quartz primaries, fused silica, which has a lower coefficient of thermal expansion, so it doesn't expand and contract or change shape as much as the temperature changes. That's important when you have sites maybe on mountaintops or in the desert where you have huge temperature gradients. And they use a dielectric coating, which is, again, if you're at least in the visual spectrum, you're covered from 400 to 700 nanometers. But it's very popular to either use that in the visual spectrum or to have the optics stripped and coated in protected aluminum, single layer, or protected gold for infrared work. And the RCs are a great design. It was designed in the early 1900s. The Hubble is an RC. The 200-inch Hale at Palomar is an RC. It was probably one of the best designs that was available without modern computing. It's fantastic for science because the aberrations that it does have, astigmatism and field curvature, don't change the position of the star. So even if it makes the star wider and less focused on your CCD sensor, you can still take an accurate measurement of that star or that satellite.
What are the figures on the optical surfaces? Are they spherical, parabolic? How are they different from a Schmidt-Cass?
A Ricci-Chretien is actually a dual hyperbolic system. So both mirrors are hyperbolic. It makes the collimation aspect very critical. You need to have both optical centers pointed at each other. We actually have a video on our OPT YouTube on how to use a laser collimator to properly align the optics. But it has a wide, flat field. You don't have to buy additional optics with, say, a 10-inch 10-inch RC can pretty much cover anything up to about an APS-C size sensor, which is about 2/3 of a 35 millimeter chip.
That's amazing.
Pretty good.
How much is a 10-inch RC?
The 10-inch truss RC is $29.95. But check out our website coming up shortly. I can't spill the beans on this just yet, but we've got
Friday sale.
There you go. You said it, not me.
Now these have quartz primaries, you said?
Yeah.
So
yeah, they do that
piece
on
of quartz?
Yeah.
Wow. That's changed because used to be everything was Pyrex, right?
Yeah.
But that's really changed.
Expands too much though.
Yes.
Yeah. As you get larger, it does. And the source that we have is able to buy the substrate in bulk and get a very, very good figure on the optics. Now, I'm not going to promise that they're going to compete with a higher end product like the PlaneWave.
Right.
But a lot of times people focus on wavefront to the detriment of other factors. They're so focused on getting the best optic that they neglect to consider things like what are the thermal properties of the telescope? Is it going to take too long to cool down or equalize after nightfall? How good is my mount? What's the seeing at my location? And also how robust is the telescope and how well does it hold optical alignment? You know, having something that looks good on paper is, a lot less important when you're trying to run an automated supernova survey every clear night of the year and you just need it to work. So, it is a workhorse telescope. And they actually have been very popular for pro services customers.
And who manufactures these again?
This is we actually OEM them through a company called TPO.
Okay. Yes. Okay, but these are OPT telescopes or telescopes. Okay, gotcha. Right.
Mm-hmm.
Fantastic.
So, getting back to this topic of hyperbolic surfaces and computer, this was the best design before computers. I don't see how you make without a computer a very good hyperbolic surface, but I guess there were RCs way before computers, and
there were.
So this must
Mr. Ricci. Yeah, Mr. Ricci and Mr. Chretien came up with a design in 1910.
1910. That was a good year. That was also around the time Hubble did his thing. And Einstein was recently finished with his big work, not so many years before. Okay, so I want to go. I want to finish up with this one topic. Getting back to the trickle down thing. One of the things that I've noticed in the professional ground-based astronomy world is there are now two. Well, there's one ground-based telescope and one space-based telescope being built on an off-axis design. This is where the primary is unobstructed, and it has an off-axis secondary that is focused, as the name implies, off of the axis of the primary, and then sent down to the instrumentation. This has the advantage of getting the primary out of the way, so things like diffraction rings, and you get more light collecting area. You get the full primary for this. The DKIST solar telescope being built on Maui right now is off-axis, and I believe the Origins Space Telescope is going to be off-axis if it's selected by the Decadal Survey. So, is there any trend toward this in the professional pro-am market, I guess? Are you seeing down maybe the possibility of some off-axis telescope designs coming down?
There is the possibility. Actually, funny enough, in the amateur telescope making field, where there's a lot of people with an optical background just going and grinding glass in their garage and putting things together, there actually have been a number of off-axis designs that have come out over the last 20, 30 years. I can't even pronounce half of them, like a tri-Schiefspiegler or things like that, where they have very weird-looking configurations. I had an optical engineer come up and talk to me at a trade show a couple of years back about his idea. He'd gone so far as to get a patent on it for, I think it was about a 13-inch f11 off-axis. Had something like 4 mirrors and 3 or 4 lenses in order to achieve a wide flat field at the focal plane. The hardest part here is just when you're dealing with manufacturer, if you're building one of something, as you are for a lot of these professional observatories, then you're going to not spare the expense. You're going to design it to meet the need. When you want to make not one of something, but 100 or 1,000 of something, then you really have to, take a look at how much does this actually cost to produce, because things start to get really complicated. If you took something like a normal parabolic mirror, anything non-spherical, and you want to do an off-axis portion of that, you can't grind it like you grind a normal parabolic mirror. You essentially have to grind it like you're doing just the left half of a parabolic mirror.
Right.
And so the math gets tricky. The way of mounting it, you have to mount it at a non-standard angle. You don't have the mirror cell at the back of the telescope. You have the mirror cell now at whatever the conic angle of that mirror is. So it could be tilted 7.8 degrees or something. And now you have to deal with structurally supporting that mirror so it doesn't shift or doesn't move, doesn't sag under the weight at an angle where it's not, you don't get the same engineering stability that you do with a more conventional system. So I think what it really comes down to is when a system becomes that complex that you almost have to hire a full-time engineer just to keep the optics aligned, then there have been a couple cases. It just comes down to it's one of those fields that hasn't realized its potential yet, I think, because of the high cost per dollar in doing that. The one commercial off-axis reflector I recall was about a 3.6 inch system, which cost around $1,000 or $1,500. It's a 3.6 inch.
Yeah, I know. I think it was a tabletop. It was really quite beautiful, actually. If it's the same one I'm thinking of.
But when you have an institution or an amateur that has an inclination to do that, then they have to think, at that price, I can get an apochromatic triplet refractor, which is truly unobstructed, and I don't have the issues of optics being mounted at weird angles.
So it sounds, sure. So it sounds like what you're saying is that the advantages of an off-axis design are not offset by the complications of putting it into a mass production.
Exactly.
So,
if you want to mass produce it, it becomes a problem. Just because what happens when you get 10% of them where the mirror cell has a flaw in it, or something like that.
Okay. Yeah. So, well, it was an interesting idea, but you're right. I have seen amateurs build them, off axis, but they've ground all the optics themselves. Superluminal. Quick question. How large an aperture would you need to detect exoplanets? I think, Tony, you once mentioned that someone did it in a parking lot with a 16-inch mead. That's true. So this is something I'm testing, by the way, folks. Now that I've got a partnership with OPT, they're going to give me access to these telescopes, and I'm going to see. We're going to go to some of these exoplanet stars and systems, and we're going to see if we can measure some light curves. But to answer your question, let me ask Chris. If I wanted to measure a dip in brightness on the part of about 1 in a billion, which it can be done with certain systems, like in the case that I know about where I was working at the High Altitude Observatory, and Tim Brown, one of the astronomers there, had a observatory in the parking lot where he used it to measure one of the first exoplanets ever discovered. It was HD something or other, but it was a hot Jupiter. It was big, and but it did prove the concept of the transit method. So I guess my question is, would you, if I told you I wanted to do some of this, as a professional, what advice would you give me from OPT?
Well, generally, if you're looking at the possibility of doing this, you can do it on bright stars with a fairly small system, with
bright
cameras
stars and large
software
planets.
algorithms. Yeah, exactly. Bright stars with large planets. Generally, from what I've heard, I read an article on it a while back, and they said it is possible to detect exoplanets down to around, say, 13th, 14th or stars on 13th, 14th magnitude with the eclipsing exoplanets of hot Jupiters with something similar to an 8-inch to 10-inch system. However, that star is going to have to be fairly bright, meaning it's going to have to be generally fairly close to us in order to do that. The main reason for going to a larger aperture system is it gives you a much wider range of targets to choose from. You know,
and the integration times on your camera would be a little bit
exactly. That's a key point as well. And so when you are focusing much more light at the camera, then you're right. You can lower the integration time. You can now utilize some of these active optic systems to keep the star on the same point more, which allows you to get a tighter focus and a better reading in less time. Generally speaking, if somebody was really going after specifically transiting exoplanets, I would probably nudge them toward a minimum 16 to 20 inch system, just because I know, you don't want to get them a system that can look at one exoplanet. If it can't detect the fainter ones, then you're putting a huge roadblock on the usability of that system. You can have a proof of concept and say, I measured an exoplanet with a 4-inch refractor. Well, great. But the next time something comes up, it's going to be too faint for you to detect. So I would generally say, that's about the range, half meter and up for specifically if all you want to do is exoplanets. I would definitely say that the larger aperture, largest aperture you can afford for your institution's budget.
What size scope do you have there at Towson, Christian?
So we have a 0.4 meter, 16 inches.
There you go. So
that's our aperture.
So, Christian, don't you think this is a great idea for a project to try, at least for students?
I think we should definitely do that. Yeah,
I want to do for exoplanet light curve research what AVSO has done for variable star observing. I think the more people you get measuring light curves, the better. You could help confirm candidates. You could refine sizes and the properties of stars in orbit around it. I think people.
Yeah, that's a great thing about exoplanets. You don't have to have the largest. Although you're right, Chris. The point's well taken. Yeah, the more aperture, the more options.
Okay, we're out of time. I'm sorry, we interrupted.
We do have one final question that we need to get to. Peter Quinn was asking. Peter, I think Peter's in the UK. Yeah, and Chris, you said that there were some restrictions on where you can sell overseas. If you could not sell in a given country, first of all, can you operate in the UK?
We have a number of systems that we can, and that's UK is one of our closest allies, as seen by our government, as seen through history. So I'll say that in general, we do take international sales on a case-by-case basis if it's a large dual-use system. However, a lot of things aren't restricted at all, and I would encourage Peter and anybody else who's considering it to just reach out to us, contact us at Pro Services. No problem. Pro Services at optcorp.com is our list, and that will get you in touch with myself and my team. Just ask us questions. We're here to answer the questions, get you a system.
Yeah, I can imagine the devil's in the details.
Shop OPT. They'll take care of you.
All right.
Shameless plug.
James Dugan's asking, when am I going to do a remote observation session? Soon. Wow. And I think probably sometime in December, which brings me to the end of this. We're definitely past time. So we're going to have to cut it here, folks. I want to thank, my guest today was Chris Hendren from OPT, the professional division of OPT Telescopes, who was telling us about the interactions between their company and the professional arm of astronomers and the things that you can get off the shelf. This will be the last hangout that we do until after Thanksgiving. We'll be back in, I think it's 2 weeks. I don't have the calendar in front of me, right, Christian? We'll be back starting this week with another Telescope Talk Pro, where I think our guests are members from LSST.
Large Synoptic Survey Telescope. Yep.
That's right. And we will be talking about that survey coming online here in the coming years. And that's something I'm particularly excited about because they're going to be imaging the entire sky several times a week. So we will be talking about them the next time we're back. I'm going to go on a small trip, and then I'll be back after that. So that is it for this, Christian. And next time we're going to have this sorted. We will also be co-streaming on Christian's YouTube channel. We'll test it beforehand. I thought this would just work. It didn't. I should have known better. So we'll do this. So
testing it was actually probably a good idea. You know.
Yeah. Well, we just just didn't get there. So So we'll be live streaming on both channels. Hopefully next time. So anyway, thanks to all of you for watching, and as always, keep looking up.
Bye-bye.
Bye.